Question 9 of tutorial 4. Here is our differential equation. It is linear and homogeneous of the second order. In addition, we are assuming that the coefficients A, B, and C, they are all positive numbers. We're supposed to show that for any solution y of x for our differential equation, we always have that this limit holds true, that the limit as x tends to infinity of y of x equals to 0. This is to say, as x gets extremely large, the solution is such that the value of y approaches 0. To prove this, we make use of the key theorem once again. We compute the characteristic equation, and using the famous formula, given the coefficients, these are the roots of our characteristic equation. Our discriminant b squared minus 4ac will be denoted by d. Using the value of d, we can split into various cases and consider the number of roots and whether they are real roots or complex roots. In the first case, let us suppose we have two distinct real roots. This means the discriminant d has got to be positive. It means, by our key theorem, where we are in case 1. So this must be the general solution. C1 and C2 are arbitrary constants that are real, and as you see, the powers of the exponential terms involve the roots. D, as we said, is whatever is inside the square root. Here is something that we note. B is clearly greater than b squared minus 4ac. It is because we understand a, b, and c are all positive numbers, and therefore we are subtracting a positive number from b squared. So this inequality holds true. b squared minus 4ac is the discriminant. Therefore, it follows that we have b squared greater than d. We square root both sides, and so we have b greater than square root of d, which is still a positive number. From this, we see immediately that minus b plus square root of d is a negative number. Similarly, we understand that minus b minus d is also a negative number. What does this mean? It means that when we look at our general solution, the powers are negative when x is positive. This term, because a is a positive number, is negative. That comes from this part. And for this term, it is also negative by this part, and because a is positive. Therefore, seeing that these two terms are negative when x is positive, it means that when we are taking x towards infinity, we are making x large and positive. It follows that these two terms, which are the only terms that involve x are going to tend, as we take the limit, to 0. That is to say, the limit of this first term would be 0, and the limit of this second term is going to be 0. We immediately have proved that the limit as x tends to infinity of y of x equals to 0. So we have proved it in this first case. Now we go on to the next case. Let us suppose we have one real root. It means that the discriminant must be equal to 0. And that's when we have a single real root. What is the root? It's just minus b divided by 2a. That's our root. So we are in case number 2 of our key theorem, so that this should be our general solution. Again, in the powers, here the root is present, but as you can see, it must be negative. Again, this follows from our assumption that b and a are both greater than 0, and we have a minus sign here. Therefore, we see that the limit of this term, the exponential of minus b divided by 2a times x, is going to be 0. What about the second term? For the second term, we first re-express it as x divided by e to the power of b over 2a times x. Then notice that the numerator tends to infinity as x tends to infinity, and the denominator also tends to infinity as x tends to infinity. What sort of rule should we apply in this case? It's written here, L'Hopital's rule. L'Hopital's rule tells us that if we know that the limit as x tends to, in our case, infinity for the numerator, and it equals to, as x tends towards infinity of the denominator, equals to 0, or in this case, where both of these terms, taking the absolute values, equal to infinity, then the limit as x tends to infinity of the quotient equals to L, where L is this limit, the limit of the quotient of the derivatives. So we apply this rule and we see that the derivative of the numerator is 1, and this is the derivative of the denominator. We differentiate both top and bottom. But now with this formula, you see immediately that the limit must clearly be 0. And that shows us that in our expression, as we take the limit as x tends to infinity, these two terms tend to 0. Therefore, the whole term is going to tend to 0. And so we have proved that in this case. Finally, let us consider the last case, when the discriminant d is negative, less than 0. In this case, the two roots are going to be given in this form. Here is where we have the real part, minus b divided by 2a, and the imaginary part of one of the roots is going to be square root of absolute value of d divided by 2a. I is on the outside. I is taken to be square root of minus 1. Therefore, we are in case number 3 of our key theorem. So this should be the general solution. You can quickly check. E, the exponential, must involve the real part, and the imaginary part, which is this, is inside the cosine function and the sine function. We are having the absolute value of d, but d is given in this form, it is negative. Therefore, what we should have on the inside must be 4ac minus b squared minus d divided by 2a. Of course, we have to take the square root of 4ac minus b squared. What is the next step? Here, we are going to make use of the squeeze theorem for limits. We understand that cosine of x is bounded from below by minus 1 and bounded from above by 1. It is also true for sine of x. This is right for all values of x. Using this fact, we can move on to apply the squeeze theorem. How can we do this? We understand that the expression involving cosine and sine is this bit. What we also know is that the exponential term here tends to 0 as x tends to infinity. That comes from this particular formula that we have found in part 2. So we need to find bounds on this portion, and we can do it. But instead of just having C1 and C2, we have to use the absolute values of these numbers. Then we see that we will have that this portion is going to be less than or equal to absolute value of C1 plus absolute value of C2. Why is this the case? It is because C1 and C2 are arbitrary real numbers. They could be positive, but they also could be negative. What we then know is that regardless of whether they are positive or negative, such an expression coming from our inequality over here must satisfy that it is less than or equal to the sum of the absolute values of C1 and C2. In a similar way, we see that we also obtain a lower bound. So we have to introduce absolute value signs to account for this fact. Now once we have this, you can see that the next step should be to apply the squeeze theorem. Multiply now this inequality throughout by e to the minus b over 2a times x. Well, we multiply it everywhere, and we see that as we take the limit, as x tends to infinity, the limit of the right hand side is going to be 0. It's clearly going to be 0. This is just a constant number. So the standard limit laws would tell us that this limit just depends on the exponential term. In a similar way, we conclude instead minus of absolute value of C1 minus absolute value of C2 is also going to be 0. So by the squeeze theorem, the solution here is always going to be bounded by two terms, and taking the limit as x tends to infinity of the two bounds will give you 0. So the squeeze theorem tells us that the limit of y as x tends towards infinity must also be 0 using the squeeze theorem. And that is precisely the solution to this question.